My name is Sean McDonald. I am the payload operator as well as the software team lead. I am a junior pursuing a computer science degree, and this is my third year on the team.
Hi, my name is Camille Kolkowski, and I am currently a junior pursuing my bachelor's degree in aerospace engineering with a specialization in aeronautics. I have 6+ years of unmanned aircraft experience as an aircraft commander for the RQ-7 Bravo Shadow with the United States Army National Guard. This is my first year in the competition as a member of the airframe team, and I will be serving as the air boss for the competition.
Hi, my name is Hunter Tedrick. I am the internal pilot for Embry-Riddle's competition team. I'm currently a junior studying unmanned aircraft systems science with a concentration in operations. I hold about 6 years of experience with autonomous and manual flight, so I'm excited for the competition.
I'm Dallas Sovak. I have 10+ years of unmanned aircraft experience in both autonomous and manual flight. At competition, I'm serving as safety pilot as well as team lead and aircraft construction lead. I am currently a junior in a bachelor's degree for unmanned aircraft systems science, specializing in UAS operations. Our system utilizes a Make Flight Easy believer airframe with a length of 42 inches and a wingspan of 77 inches. The airplane's twin motor configuration, paired with high-pitched props and low kV motors, allow for an aerial mapping combination fit for efficient, long-endurance flights. As opposed to their previous year with the Jetson TX1, this year we're using the NVIDIA Jetson TX2. This new computer employs twice the performance and better power efficiency over the previous TX1. This allows us to process higher resolution imagery faster in real time onboard the aircraft, improving target detection accuracy. The batteries we're using for this airframe are Aptus Aerospace Grid 6-cell lithium-ion batteries used in parallel. These batteries give us an endurance increase over traditional lithium polymer setups. This is another huge contributing factor in the increase of our aircraft's flight time. As opposed to last year's 2.4 GHz model, we have upgraded to a Bullet M5. At 5 GHz, it has a higher bandwidth, increasing our data rate. Being a less populated frequency than 2.4, it adds resilience to the signal and would be less polluted. Our directional autonomous antenna tracker locks onto the Bullet M5 with surprising accuracy and will not interfere with our 2.4 GHz control system. Our downward-facing imaging sensor is an Econ Systems C3 Cam 12-megapixel camera. It has a form factor of only 3 centimeters cubed and weighs only 20 grams including the lens. This camera utilizes a USB 3 connection, which allows for direct integration with the Jetson and faster data rate, giving us higher resolution and higher frame rate. The NVIDIA Jetson also has native support for this camera. The autopilot we're using is a Pixhawk-based Pix Racer. This lightweight autopilot has an extremely small form factor, more telemetry ports, and better connectors compared to a traditional Pixhawk. Paired with a 3DR GPS module, the aircraft performs reliably every time it takes to the skies. The antenna tracker utilizes a directional antenna for a 5 GHz ubiquity rocket that gives the aircraft a potential range of several miles beyond mission requirements and line of sight. It pairs perfectly with the aircraft's onboard omnidirectional patch antenna. This tracker uses a servo controller and integrates directly with Mission Planner to operate, reducing complexity and room for failure in regards to the system. The believer airframe employs a quick-release wing connection system that allows the team to quickly assemble and disassemble the aircraft at the field. The skid plates on the bottom of the aircraft protect the camera and fuselage from damage when landing on rough surfaces. For takeoff, the aircraft can be safely hand-launched and can utilize the lightweight skid plates instead of landing gear that typically cause more drag. The ground station is comprised of 2 military-grade laptops, a Pelican case housing a networking system, a power source, and an antenna tracker. This system has been optimized for quick assembly and disassembly for field operations. The laptops receive power from the payload case, and their batteries act as a backup power source in the event of power failure. The payload case is cooled by 2 variable speed fans and operates as a closed unit with external I/O. The laptops run the camera software, MapLink, Mission Planner, and the antenna tracker controller. For the planned tasks, the team plans to complete the competition completely autonomously. This includes flight, image capture, image transfer, target detection, and obstacle avoidance. However, the team will omit the air delivery portion of the competition. We have done 8 major types of testing for our unmanned aircraft system. This includes image, airframe, weighted, fail-safe, vibration, endurance, autonomy, and mission simulation. These different types of testing were done to ensure the aircraft would be ready for competition and we wouldn't have any sort of anomaly happening. For the image testing, this tested image detection and image capture, as well as the resolution we're getting and if we can actually identify the targets. This let us know that the actual imaging system on the aircraft is ready for competition. The airframe testing involved taking the actual airframe and base electronics and flying it manually in the air to ensure the aircraft was flight ready. Once the aircraft was flight ready, we then moved to weighted testing, which simulated an actual payload on the aircraft to ensure that the airframe was capable of carrying a payload of that weight. After that, we decided to move on and to adjust the PICSOC and do fail-safes. The fail-safe testing allowed us to make sure that if the aircraft was in a situation such as an emergency, we could get the aircraft back and could perform the fail-safe procedure properly. Vibration testing was done in order to ensure that the camera's rolling shutter didn't have a big effect on the images that we captured. The vibrations of the aircraft and the motors have the capability to actually throw off the camera's sensor. For endurance testing, the aircraft demonstrated that it is capable of flying the competition limit of 45 minutes. This allowed us to make sure that the aircraft could fly the entire duration of competition should the need arise. The next type of testing, autonomous testing, is probably one of the most important for the competition. A number of autonomous flights were performed to ensure that the aircraft was tuned and could perform the deliverables reliably. This was one of the most important tests, as the aircraft will spend all of its time in this mode. Mission simulation testing incorporated autonomous flight heavily, however it also allowed us to evaluate the team's readiness in regards to operations, communication, and crew resource management principles. At this time, we've flown 22 flights that included autonomous operations. 86.47% of that flight time was fully autonomous, while 13.53% was manual flight. After airframe testing with the autopilot, we concluded that major additional tuning to the autopilot was not needed, as the aircraft flew predictably with the standard mission planner parameters for a VTOL aircraft. For waypoint accuracy, in many hours of autonomous testing, we can confidently say that our aircraft can fly consistently within the 100-foot boundaries of the waypoints it follows. Out of the 55 waypoints we specifically tested for this, we successfully hit 45. We had found that the waypoint errors were caused either by waypoints being too close or winds in excess of 17 knots. For obstacle avoidance performance, we have been able to manually plot waypoints around designated stationary obstacles without any issues. And for imaging, we've done live in-air testing and processing that was performed to verify data rate and image capturing capabilities. We then took the collected data and continued tuning the algorithm on the ground during post-processing. The average resolution of each cropped image is about 100 pixels squared. We specifically chose the camera, lens, power setting, and altitude to give us proper ground resolution to resolve targets to the best of the system's ability. For detection and classification, we have a high confidence detection and medium confidence of localization. We have a very high confidence, however, in manual classification of images. We have also been able to localize targets within an average of 15 to 20 feet. Out of the 2 mission tests we've tried, the aircraft has demonstrated it is capable of completing the planned tasks. Early on during testing, we found that the vibrations during maneuvering and high power settings were creating a rolling shutter effect in captured images. This was mitigated by remounting the hardware with vibration dampening materials and ensuring props were balanced. We also had to adjust the autofocus feature on the camera to keep the exposure at an acceptable level. The aircraft is able to fly within the set boundaries and waypoints that we set to simulate the mission and perform this autonomously. We experienced complications arising from GPS drift during autonomous landing involving a manual takeover. We also lost points during simulated missions with geolocation and autonomy errors. Adding this onto the amount lost from moving obstacles and air delivery, we have scored ourselves at the moment with a 73.8% in simulated missions. I'm Team Lead Dallas Slovak for the Embry-Riddle Aeronautical University, and I'll see you guys in a bit.